Okay, so we will continue studying the properties of Lebesgue measure and some Lebesgue sets. In the last lecture, we saw how it behaves with respect to the linear transformations, and we have seen some invariance properties earlier, like it is translation, the Lebesgue measure is translation invariant, it is invariant under dilations, it is invariant under reflections and so on. We will see that they give us some change of variables formula which you are familiar with when you studied Riemann integration, you have seen such things. Okay. So, they sort of continue to hold true here with some justification. So, let me elaborate on that a little bit. So, we start with invariance properties of Lebesgue measure. So, invariance, recall that measure of E plus x equal to, so let us put x naught equal to measure of E, right. So, this was true for every E in the Lebesgue set on R k, and x naught was a point in R k, right. So, we had this from the beginning. Well, I want to say this gives us some kind of change of variable formula. So, let us see what does it say. It says that, let us write this in terms of integration, since we know that measure of the set. So, in any triple we started with the measure of a set E, right, is equal to the integral of the indicator of E, right, whenever E was a measurable set, of course, right, and this was the basis for everything. Okay, this gave us integration for simple functions and by taking limits for positive functions and then for all functions. So, we can use the same technique. So, well, how do we do that? So, let us look at the left hand side. So, what is the left hand side? Left hand side is the indicator of E plus x naught, and then you integrate over R k with respect to measure mu, sorry, the Lebesgue measure, right. So, we have the Lebesgue measure dm. On the right hand side, it is simply the integration of chi e with respect to Lebesgue measure. Okay. But let us look at this function. What does this mean? How is this defined? So, indicator of E plus x naught at the point x is, well, it is 1 if x belongs to E plus x naught and 0 otherwise, which is same as it is 1 if x minus x naught belongs to E and 0 otherwise. So, the left hand side I can write as integral over R k chi e, right, chi e of, let us say, x minus x naught dm x. So, the x is put to say that x is, the integration is with respect to the variable x. This is equal to integral over R k chi e. So, let me write chi e of x dm x. So, this is something which you have done in Riemann integration. Okay. So, changing the variable x minus x naught to y and so on. Okay. So, this tells me that we have some formula for indicator functions, right. So, by linearity this extends to non-negative simple functions, right, because so if f is s is a simple function, it is a linear combination of indicators, right, and integral is linear. So, we will have, so suppose s is a simple function. Okay. So, then from here we get integral of R k of s of x minus x naught dm x. This is equal to integral over R s of x dm x. So, I am putting the x to indicate that the integration is with respect to x. So, now this is true for every simple function positive. So, now I can apply monotone convergence theorem. Apply monotone convergence theorem. If I take a positive measurable function, there exists a sequence of simple functions which increases to that. So, that will tell me that on both sides I have convergence to f of x minus x naught dmx equal to integral over r to the k f of x dmx. So, this is precisely the translation invariant property of the Lebesgue measure. Okay. So, this is true for all positive functions for every f positive measurable and by linearity to all functions whenever the integrals exist, of course, to all measurable functions whenever the integrals exist. So, you have seen this for Riemann integration and it continues to be true for Lebesgue integration. So, we used translation invariant property, but let us go back to the general thing we just proved. So, maybe I will take a new page here. Okay. So, if t from R k to R k is linear and invertible, okay, then we know that measure of T e is equal to modulus of determinant of t times measure of e. This is what we just proved. So, let us write that in the integral form. So, this is integral of R k chi of T e, right. So, I will put the x just to indicate that integration is with respect to the variable x, because we will be changing the variable now. Determinant t integral over R k chi e of x dmx. But let us look at the left hand side. This function, what does that mean? Chi t e of x equal to 1 if x belongs to T e, 0 otherwise, which is same as. So, I want to say that it is 1 if T inverse of x belongs to E and 0 otherwise, right. So, this is a better way of writing. So, the left hand side integral is simply integral over R k chi of E now, but T inverse x dmx. Okay. This is equal to modulus of determinant of t times integral over R k chi E of x dmx. Good. So, now we can do the steps we did earlier, change chi e to simple functions, right. So, change chi e to simple functions and use monotone convergence theorem etc. to get integral over R k. So, I will write the general result now. F of chi e becomes s, a simple function, and s becomes a measurable function f, right. T inverse x dmx equal to modulus of determinant of t integral over R k chi e x, sorry, f x dmx. Okay. So, maybe write it in a slightly better form. So, call T inverse something else. So, call T inverse equal to the linear transformation A. Then what we have here is integral over R k f of A x dmx equal to determinant of T. So, T inverse is equal to A. So, determinant of T whole inverse is equal to determinant of A, right. So, I can take this to the side and I will get modulus of determinant of A equal to integral over R k f x dmx. So, this is the usual change of variable which you are familiar with. So, what do we do whenever we have something like this? We put A x equal to y, and the change of variable should tell you that determinant modulus determinant of A dx is dy, right. So, you can change everything to y variable and you will get whatever is on the right hand side. Okay. So, let us move to a slightly different kind of result. So, this is about sets which are small. So, let us talk about Cantor set. Well, what is Cantor set? So, let us take 0 1, divide this into 3 equal parts, okay, and then you throw out the middle 1/3 interval. So, you leave this, okay. So, you have thrown out the interval 1/3 to 2/3. Now, you continue this process. So, you have 0, 1/3, you have 2/3 and you have 1. Okay. You make them again, you take the middle 1/3 and middle 1/3 here. So, what does it mean to say middle 1/3? You divide each interval into 3 equal parts and throw out the middle 1/3. Okay. So, this would be 0, 0/3 square if you like, 1/3 square, 2/3 square and 3/3 square is 1/3. So, you are throwing out this. Okay. So, 1/3 square to 2/3 square. Okay. Similarly, another interval. So, you can find out what these are. So, you have thrown out 2 intervals of length 1/3 square. Here you have thrown out 1 interval of length 1/3 and so on. Okay. So, nth step you will be throwing out 2 to the n minus 1 intervals, open intervals of length 1/3 to the n. This is what you will be doing. So, at each stage, so let us call this C1, let us call this C2, etc., etc. I have Cn and so on. Okay. So, I continue this infinitely many steps. So, I have C1 which is bigger than C2 because I am throwing away things from C1, right, and I throw away from C2, etc., etc. What do I know about them? Each C1 is closed, right, C2 is closed. Well, let us see why are they closed, because we are throwing out the open intervals. So, C1 is this closed interval union this closed interval. Similarly, C2 is a union of 4 closed intervals, right. Each time we throw out an open middle third. So, what remains is closed. So, this is a decreasing sequence of closed sets in a complete metric space. So, the intersection cannot be empty, as you know. So, the intersection Cn. So, this is a closed set. Okay. So, this is what is called the Cantor set C. Okay. So, Cantor set C has various properties which you would have seen in real analysis. So, I will not get into the proofs of any of this. Cantor set C has various properties. One, C is closed, of course, because the intersection of closed sets, bounded because it is inside 0 1. So, compact. So, that is a compact set. 2, C is uncountable, it is an uncountable set. 3, C has no interior, has no interior points. Okay. In other words, C is nowhere dense, C is nowhere dense, and C is a perfect set. C is a perfect set. What does that mean? That means every point in C is a limit point of C, is a limit point of C. Okay. So, these are interesting properties of the Cantor set. It is one of the most interesting sets you will encounter. You can modify this construction, but right now let us stick to C. So, let us go back. What did we do? We threw out middle 1/3 at each level, right. So, at the nth level we will be throwing out 2 to the n minus 1 intervals, open intervals of length 1 by 3 to the n. Okay. So, if you look at the Cantor set C and look at the set 0 1, everything is inside 0 1, right, and look at the complement, okay, and measure of this, everything makes sense, right. C is a closed set, the complement is open. So, measure of that will make sense. Well, what is the measure of whatever is thrown out? Well, you will start from adding here, then you add this, then you add this, and so on. All these are disjoint open intervals, right. At nth level you have 2 to the n minus 1 disjoint open intervals, and each level the open intervals are disjoint from the previous ones. So, all that you have to do is to add this quantity and see how much you get, right. So, this is simply the sum of 2 to the n minus 1 by 3 to the n and going from 1 to infinity, right, because of countable additivity, and this is 1. So, you have thrown out open intervals whose length adds to 1. What does that mean? Hence, the measure of the Cantor set C, even though it is uncountable, is 0. So, this is one example of, uncountable set whose measure is 0, whose Lebesgue measure is 0. Of course, if you take a countable set, it has measure 0, right. So, this is one example where the set is uncountable, but its Lebesgue measure is 0. Now, recall that the Lebesgue sigma algebra of the real line with respect to the measure m is complete. Okay. Hence, any subset of the Cantor set is measurable, because Cantor set has measure 0. So, any subset of the Cantor set is measurable, because measure of m is 0, measure of C is 0. So, that gives us lot of sets in the Lebesgue sigma algebra. Okay. So, let us compare the Borel sigma algebra of the real line and the Lebesgue sigma algebra of the real line. Okay. Now, this is countably generated. What does that mean? So, generated by open intervals a b, where a and b are rationals. So, there are only countably many such open intervals, and that generates b of r. Okay. From this it can be shown So, I am not proving any of this, this is simply an assertion. From this it can be shown that B of r, the cardinality of B of r is C. So, the small c is the cardinality of the real line, uncountable, okay, first uncountable number if you like. But at the same time, if you look at the Lebesgue sigma algebra of R, that has too many sets, because the Cantor set C, capital C, belongs to Lebesgue sigma algebra of the real line, and the cardinality of C is uncountable, right, uncountable, because it is an uncountable set. So, that is the small c. So, capital C has 2 to the small c subsets, all of them belonging to the Lebesgue sigma algebra. So, let us recall. So, here we have B of r having cardinality C, here we have L of r with 2 to the c subsets sitting there anyway. So, the inclusion, so there are, so from this cardinality argument, so there are subsets or there are sets which are Lebesgue sets, Lebesgue measurable, but not Borel measurable, right, from the cardinality argument, because here you have only C many set, but for L of r we have 2 to the C many set. So, there are too many sets which are not Borel, but Lebesgue measurable. Of course, this is one way of proving this. We will, so later we will construct using some other again using Cantor set and the Cantor function, we will construct a example. Okay. So, I will do this later. So, later we will construct using Cantor set and the Cantor function So, I will explain what that is when we do the construction. Construction is not very explicit, it is just proof of the existence. Okay. So, not using cardinality argument. So, construct meaning proof of existence using Cantor set and the Cantor function, sets which are Lebesgue, but not Borel. Okay. So, let us conclude the session, but let me explain one more construction of the Cantor set, Cantor like sets. So, let us go back to the Cantor set. We started from 0 1 and then we threw out the middle thirds. So, you can modify the construction. So, I will give you a reference. So, see the book by Stein and Saccacci. So, E. M. Stein and Rami Saccacci. On measure theory. For the construction of generalized Cantor sets, So, what do you do instead of instead of middle 1/3, what you do is you remove a slightly smaller interval. Okay. So, this has to be done with some care, but you can do this and same process, okay, and same process. So, what you get is for any alpha between 0 and 1, we can construct, let us say C alpha Cantor-like set such that C alpha is of course sitting inside 0 1, C alpha is compact, C alpha has no interior, this is interesting, no interior, and measure of Z alpha instead of being 0 you can make it alpha. Okay. So, the point to note is that you can slightly modify the construction of the Cantor set and you will get some interesting sets. So, notice that the complement C alpha complement inside 0 1 is a dense open set in 0 1 of measure 1 minus alpha. Okay. So, note that. So, you can make this as close to 0 as you want. So, you have very small dense open sets which you can consider. Of course, that is not very surprising. Okay, we will stop here. In the next lecture, we will continue this circle of ideas and then use the Cantor function. So, Cantor function will be a function first defined on the Cantor set, but then you can extend it to the closed interval 0 1 as a continuous map. The point of the Cantor function is that it maps the Cantor set into a set which has measure 1, and using that and the fact that homeomorphisms will map Borel sets to Borel sets, we will justify the existence of non Borel sets, but Lebesgue sets. That is what we will do in the next lecture. Okay.